Hi everyone, my name is Xiaoling. Today, Xizhe and I will give a presentation of our work Tripoline. In many real-world application scenarios, a stream of updates are continuously applied to the graph, often in batches for better efficiency, known as a streaming graph scenario. Taking Twitter as an example, new followers are generated constantly, adding new edges to the existing graph. To get query results up to date, a naive solution is to evaluate the query on the latest graph from scratch. But for iterative graph queries, this full query evaluation can be expensive. Instead, existing streaming graph processing frameworks choose to evaluate the queries incrementally for better efficiency. Several streaming graph systems have been proposed to support incremental evaluation, like Kinograph, Nile, Tornado, Kickstarter, and others. The basic idea is that each time the graph is updated, the query of interest will be re-evaluated based on the results of previous evaluation. Because the updated batch is really a tiny fraction of the entire graph, the incremental evaluation usually converges much faster than a full re-evaluation. However, this approach requires a priori knowledge of the query to be incrementally evaluated, known as standing query. The users can only ask the same query as a standing query. Otherwise, the user query has to be evaluated from scratch. This is especially an issue for vertex-specific queries, which carry a source vertex as a parameter, like VFS, single source shortest path, single source widest path, and many others. Taking BFS as an example, if the standing query is a BFS query for vertex 5, then only the user query vertex 5 can be incrementally evaluated. If the user still asks a BFS query on a different source vertex, like vertex 7, then the query evaluation had to start from scratch, because the results of vertex 5 cannot be directly reused for vertex 7. The primary goal of this block is to lift this requirement, such as a user query for an arbitrary source vertex can be incrementally evaluated. The key to achieve this goal is a concept called graph triangle inequality. We all know the triangle inequality in the Euclidean space. The sum of the lengths of two sides must be greater than or equal to the length of the third side. In fact, a similar triangle inequality also exists in the graph space. Considering three arbitrary vertices in a graph, the shortest distance among them also form a triangle. This distance-based graph triangle inequality is well known to the theoretical graph community and have been used for graph optimizations before. More interestingly, we found similar principles for many other graph problems, such as single source widest path, single source reachability, Viterbi algorithm, and some others. For different graph problems, the operators used for addition and comparison could be different. Taking the single source widest path as an example, here, the addition becomes mean, and the greater than becomes less than. To capture all these different cases, we propose an abstraction graph triangle inequality with a generalized addition and a generalized greater than operators. Here, the property refers to any path-based graph properties between two vertices. With the triangle inequality, now we can connect an arbitrary user query U with a standing query R. Their results must satisfy the corresponding triangle inequality. After establishing the relations between the user query and the standing query, we can design a more general user query framework where the user query can reuse the results of the standing query, even when their source vertices are different. We call this triangle inequality-based incremental evaluation. Each time after the graph is updated, the standing query will be re-evaluated first. Then its results will be fetched to this triangle inequality module. The module will generate vertex initial values based on the triangle inequality and directly starts the evaluation of these initial values rather than the default initial values. As its calculated initial values must be no worse than the default initial values. In fact, often much better. The evaluation usually takes less iterations and computations to convert. From high level, the triangle inequality module serves as an adapter, which connects the user query with the standing query. For correctness purpose, in this work, we assume that the graph evaluation function is monotonic and safe under asynchronous execution. Both assumptions have been commonly referred to in existing graph frameworks for various optimizations. First, the triangle inequality ensures that the calculated initial values are valid, which means the initial values are possible states during actual evaluations of the query. Second, the monotonicity ensures that the converged values are no greater than the initial values. Then, the converged values may replace the initial values. And finally, the asynchronous safety ensures that even with asynchronous execution of the vertex functions, the converged values will eventually replace the initial values. Together, they ensure that the results from triangle inequality-based evaluation must be the same as a non-incremental evaluation. After confirming its correctness, next, I will briefly explain two complexities in making this technique more general and effective. First, for directed graphs, the paths in the triangle are also directional. In this case, evaluating the standing query does not provide the property we need for computing the initial values. To address this, we can simultaneously maintain both query R and its reverse query, which is supposed to run on the H direction reverse graph. To avoid maintaining the reverse graph, we propose a dual model evaluation scheme, which leverages both push and pull models for value propagation. In this way, we don't need the reverse graph. Another complexity in designing this technique is how the standing query should be selected. Ideally, the best standing query is the one that can minimize the initial values for all possible user queries, because the smaller the initial values are, the closer they are to the stable values. However, this requires to compute the probability between every pair of vertices, which is too expensive to collect for large graphs, not to mention in a streaming scenario. The less ideal but much simpler way to select the standing query is to maximize its reachability to the user queries. This often ensures that the calculated initial values are at least smaller than the default initial values. For such queries, we can use high-degree vertices as an approximation, which tend to have the best overall reachability to other vertices. In fact, our actual implementation is a compromise between the two selection strategies. Basically, the selection has two steps. In the first step, we select the top k high-degree vertices as the standing queries and maintain them incrementally and continuously. Then, when the user query is given, we select one of the standing queries for applying triangle inequality. And this should be the one that minimizes the property between the vertices associated with the standing and user queries. More details about the selection can be found in our paper. Next, Xizhe will talk about the implementation and experimental result of this triangle inequality-based incremental evaluation.
We implemented the triangle inequality-based incremental graph evaluation on top of an existing streaming graph engine called Aspen. We named the new system Tripoline. Aspen is a state-of-the-art streaming graph engine which supports low latency and high throughput graph updates. It maintains the streaming graph using a compression tree-based data structure and processes the graph in parallel in a way similar to LiGraph. The two new modules in Tripoline are the standing query evaluation module and the user query evaluation module. The former maintains multiple standing queries continuously and incrementally. Based on their results, the latter incrementally evaluates the user queries using triangle inequality. In addition to vertex-centric programming model, Tripoline also provides an interface for developers to specify the triangle inequality for the given graph problem. Here are some details about our evaluation setup. We run the experiments on a 32-core commodity server with 12 GB memory. We evaluated Tripoline using 8 graph benchmarks on 4 real-world large graphs. To simulate the streaming scenario, we assume that a substantial portion of the edges has been streamed in. Then the rest of the edges are inserted into the graph in batches. By default, the update batch size is 10K. As for the number of standing queries, we vary it from 1 to 64, but by default, we set it to 16. This table shows the speedups of Tripoline compared to the non-incremental evaluation of user queries. Overall, we observed substantial speedups for most benchmarks, which confirms the effectiveness of the proposed triangle inequality optimization. However, depending on the type of queries, we also find that the speedups vary a lot across different benchmarks, ranging from 1.1 to over 30 times. To further examine the variation of speedups, we measured the ratio of vertex function activations with and without triangle inequality optimization. Basically, a higher activation ratio implies less computation savings, thus lower speedup. As shown in the table, this ratio also varies significantly across graph benchmarks, which indicates that the effectiveness of triangle-based incremental evaluation highly depends on the graph problem. Taking single source widest path as an example, the activation ratio is extremely low thanks to its min-max nature of the computations. In our paper, we provide a detailed analysis on how the graph problem properties affect the effectiveness. We also conducted experiments to verify the effectiveness of standing query selection heuristic. This figure shows how the speedups are distributed across different queries. The x-axis is for the different user queries, while y-axis is for the speedups for triangle-based incremental evaluation. We can see for SSSP, BFS, and SSNSP, the speedup distributions are highly biased. SSWP, SSNP, vector B, and radii have slightly biased speedup distributions, while the distribution of SSR is almost uniform. The variations, to a large extent, depend on the connection between the standing query and the user query. To find out this connection, we profiled the correlation between the speedups and the property of the graph problem. As shown in this figure, the x-axis is for different property values from the user query to standing query, while y-axis shows the speedups for choosing those standing queries. From the results, we found that there are significant correlations between these two factors, which confirms the importance of standing query selection. In fact, the trends are consistent with our query selection heuristic that the best standing query is chosen among the k standing queries based on the specific user query. For example, in the case of SSWP, the heuristic is to select the query that maximizes the path width, which is exactly the one that achieves the highest speedup. Although Tripoline is implemented based on Aspen, the idea of triangle inequality-based optimization may also be adapted in other streaming graph systems. To demonstrate its generality, we examined the potential of applying it to a state-of-the-art general-purpose streaming framework called differential data flow. We chose the latest version of DD, which supports graph index sharing among queries, referred to as shared arrangements. To integrate the triangle inequality optimization, we added a filter to its graph processing data flow. The filter uses triangle inequality as a predicate to prune the downstream reduce operations. We then evaluate 3 query benchmarks on LiveJournal and Twitter graphs. The effectiveness of the triangle inequality optimization in DD can be reflected by the number of invocations of the downstream reduce operator, as shown in the table on the right side. In general, we observed similar performance benefits. In conclusion, we found that graph triangle inequality is a common property for many vertex-specific graph problems, and it is a key to enable a more general graph query incremental evaluation scheme. Based on this principle, we built Tripoline on top of an existing streaming graph engine and observed substantial performance improvements for a range of different graph queries. Thank you for listening, and we are happy to take any questions.